Welcome to Lesson 9.6, Optimization and Scaling. Learning Objectives. This is the capstone lesson of the Production Deployment module, and it's where everything clicks. You'll master performance optimization techniques, cost reduction strategies, and scaling patterns that take your fine-tuned model from it works to it's production ready. Budget about 60 minutes for this one. It's advanced material, but if you've come through Lesson 9.5 on CI/CD, you have exactly the foundation you need. Optimization overview. Optimization in production. ML isn't a single dial you turn. It's four distinct dimensions, and they pull in different directions. Latency is about how fast a single request gets answered. Throughput is about how many requests you can handle simultaneously. Cost is about how much you're spending per request. And quality is about whether the outputs are actually good. The techniques in this lesson target all four. Quantization and pruning to shrink your model's compute footprint for lower latency. Dynamic batching and multi-GPU setups push throughput higher. Auto-scaling and spot instances cut your cloud bill. And A/B testing with fallback strategies keeps quality from degrading under pressure. The reason you need to think about all four together is that optimizing one in isolation almost always hurts another. And the goal is a system that's fast, cheap, scalable, and correct at the same time. Part 1. Inference Optimization. The first optimization tool is torch.compile, PyTorch 2.0's built-in graph compiler. Here's the mental model. Every time your model runs a forward pass, PyTorch normally executes operations one at a time in eager mode. Torch.compile analyzes the entire computation graph up front and fuses operations together, eliminating redundant memory transfers in kernel launches. The reduce overhead mode is specifically tuned for inference, where the graph is stable and predictable. The code loads your fine-tuned model with 4-bit quantization already active, then wraps it with torch.compile. The warm-up step is not optional. It's where the actual compilation happens. The first few forward passes are slower, while PyTorch traces and compiles the graph. Every subsequent pass benefits from that work. When the benchmark function runs, watch for two numbers: average latency in seconds and request per second. The compiled model should deliver roughly 1.9x the throughput of the eager baseline, on the same hardware, with zero changes to your model weights. Torch.compile speeds up individual requests. Dynamic batching is what makes the system scale. The insight here is that your GPU is massively underutilized when it processes one request at a time. It's like running a commercial dishwasher for a single cup. The batch inference queue class fixes that by collecting incoming requests over a short window and processing them together. The constructor accepts your model and tokenizer, a maximum batch size, and a maximum wait time. When a request arrives via the inference method, it gets placed on an asyncio queue and receives a future object, a placeholder that will eventually hold the result. The process batch's coroutine runs continuously in the background, waiting for that time window to fill, then pulling up to max batch size requests off the queue and running them through the model in a single forward pass. The concurrency here is the key. The program never blocks waiting for one request to finish before accepting the next. The numbers tell the story clearly. Solo requests get you roughly 4 requests per second. Dynamic batching pushes that to 18. That's a 4.5x throughput gain without touching a single hyperparameter. Even with batching, you're still doing GPU compute for every unique request. Caching eliminates that compute entirely for repeated queries. And in real deployments, repeated queries are far more common than you'd expect. The Cache Manager class implements a 2-level strategy. Level 1 is an in-memory dictionary, zero network overhead, sub-millisecond lookup, but limited by RAM and lost on restart. Level 2 is Redis, persistent, shared across multiple server instances, and configurable with a TTL so stale responses expire automatically. The lookup order matters. Every incoming prompt gets hashed with SHA-256. That hash becomes the cache key. The manager checks memory first, then Redis. On a Redis hit, the result gets promoted back into memory, so the next identical request never even touches the network. The set method writes to both layers simultaneously. In the API flow, This cache check happens before any model inference. The output metrics show an 85% cache hit rate and a dramatic reduction in average response time. That 85% figure means 85% of your requests cost essentially nothing in GPU time, which has a direct and immediate impact on your cost per million requests. Part 2. Cost optimization. You can't optimize what you can't measure. Before you make any cost decisions, you need real-time visibility into how hard your GPUs are actually working. This script uses PyNVML, NVIDIA's management library Python binding, to query utilization and memory stats directly from the driver, then exposes those stats as Prometheus metrics. The initialization step calls NVML init and counts the available devices. Inside the monitoring loop for each GPU, it retrieves two things: the utilization struct, which gives you compute percentage and memory bandwidth percentage, and the memory info struct, which gives you used and total VRAM in bytes. Those values update the Prometheus gauges, which your monitoring stack can then scrape. The sleep interval of 10 seconds keeps the polling lightweight. Running this in a daemon thread means it never blocks your inference code. What you're looking for in the dashboard is a GPU utilization number that's consistently above 70% during serving. If it's sitting at 45%, which is the baseline in our summary table, you're paying for GPU time you're not using, and batching or auto-scaling adjustments will recover that cost. With GPU metrics flowing into Prometheus, you can now drive auto-scaling decisions from real data. This Kubernetes HPA configuration wires those metrics directly to your deployment's replica count. The scale target ref points to the ML model API deployment. The floor of 2 replicas guarantees high availability. You're never running on a single point of failure. The ceiling of 10 gives you headroom for traffic spikes without unbounded spend. 3 metrics drive scaling decisions simultaneously: CPU utilization targeting 70%, a custom GPU utilization metric targeting 80%, and HTTP request rate targeting 50 requests per second per replica. Whichever metric breaches its threshold first triggers a scale-up. The behavior block is where you prevent thrashing, the system that scales up and down every few seconds in response to noise. The stabilization. Window seconds of 60 means the HPA waits a full minute of sustained pressure before scaling up, and 3 minutes before scaling down. The percent policies cap each scaling event at either 50% of current replicas or 2 pods, whichever is larger. This keeps your infrastructure changes gradual and predictable. Auto-scaling controls how many pods you run. Spot instances control how much each pod costs. This YAML defines 2 parallel deployments that work together to cut your compute bill significantly. The ML model API Spot deployment runs 5 replicas on Spot instances, cloud VMs that are 60 to 90% cheaper than on demand, but can be reclaimed by the cloud provider with 2 minutes notice. The toleration and node affinity fields ensure Kubernetes schedules these pods exclusively on nodes with the Spot instance taint. The lifecycle stop hook with a 30-second sleep is critical. When a Spot node gets preempted, Kubernetes sends a SIG term, and this hook buys your pod time to drain in-flight requests gracefully before the process exits. The ML model API on-demand deployment runs 2 replicas on reliable on-demand instances. These are your safety net, always available, never preempted, handling traffic when Spot capacity is thin. The combined effect is a fleet that's predominantly cheap Spot capacity with a guaranteed on-demand baseline underneath it. In practice, this mix delivers roughly 42% cost savings compared to running everything on demand, with no degradation in availability. Part 3. Performance benchmarking. Optimization claims are only as good as the benchmarks that validate them. This load testing script uses asyncio and IOHTTP to fire concurrent HTTP requests at your API and measure how it actually behaves under pressure, not in theory, but under real load. The load test function accepts 4 parameters: the target URL, the total number of requests to send, the concurrency level, and the request payload. A semaphore enforces the concurrency limit. It's a counter that blocks new requests from starting until a running one finishes, so you never have more than concurrency requests in flight simultaneously. For each request, the script records whether it succeeded or failed and captures the round-trip latency. After all requests complete, it computes average latency, P95 latency, P99 latency, and throughput in requests per second. The percentile numbers are what matter most in production. Average latency hides the tail. P95 tells you what 95% of your users actually experience, and P99 tells you about your worst cases. When you run this against your pre-optimization and post-optimization deployments, the delta between those two runs is your real measured improvement, not an estimate. Part 4, A/B testing framework. Benchmarks tell you how fast your model is. A/B testing tells you whether a new version is actually better for users. The A/B Test Manager class manages that comparison by routing each user deterministically to either the control model or the treatment model. The treatment percentage parameter controls the split. Set it to 10 and 10% of users get the new model. 90% get the current one. The assign variant method hashes the user ID and maps it to a bucket. Hashing the user ID rather than using random assignment is deliberate. The same user always gets the same variant, which means their experience is consistent across sessions, and you're not measuring noise from users switching between models mid-conversation. The inference method looks at the assigned variant, runs the appropriate model, and records the latency alongside a request counter for each variant. The response payload includes the generated text, the variant name, and the latency, giving your analytics pipeline everything it needs to compare the two models on both performance and output quality. Collecting A/B test data is only half the work. The analysis function turns that data into a decision. It takes two data frames, one for control, one for treatment, and a metric column name, defaulting to latency. The function computes the mean for each group, then runs a two-sample t-test test to determine whether the observed difference is statistically significant or just noise. The p-value threshold of 0.05 is the standard cutoff. Below it, the difference is unlikely to be random. But statistical significance alone isn't enough. A difference can be significant and still be trivially small. That's why the function also computes Cohen's d, which measures effect size. A Cohen's d above 0.2 is small, above 0.5 is medium, above 0.8 is large. The printed output tells you the means, the absolute difference, the p-value, and the effect size together. With those four numbers, you can make a confident, data-driven call, ship the new model, roll it back, or run the test longer to collect more signal. Optimization summary. Here's what the full optimization stack delivers, measured against an unoptimized baseline. P95 latency drops from 480 milliseconds to 250, nearly twice as fast. Throughput jumps from 10 requests per second to 170, a 17.5x improvement. GPU utilization climbs from 45% to 82%, meaning you're extracting far more value from the hardware you're already paying for. Cost per million requests falls from $85 to $20, a 7x reduction. Cache hit rate goes from 0 to 85%. And error rate drops from 0.5% to 0.08%. None of these improvements required changing your model weights or retraining anything. Every single gain came from how you serve the model. Compilation, batching, caching, smart instance selection, and auto-scaling working together as a system. To map each number back to its source, Torch.compile delivers the 1.92x latency improvement. Dynamic batching is responsible for the 4.5x throughput gain. Multi-level caching produces the 85% cache hit rate. Spot instances account for the 40% cost savings. Smart auto-scaling drives GPU utilization from 45% to 82%. And the A/B testing framework gives you the feedback loop to keep improving all of these numbers over time without guessing. Course completion. Congratulations. You've finished the entire fine-tuning course, all 9 modules, environment setup, LoRa AI, and dataset preparation, basic fine-tuning, advanced techniques, evaluation and iteration, specialized topics, real-world projects, and production deployment. That's roughly 300,000 words of content across 48 lessons, Every technique calibrated for your two Tesla P40s with 24 gigabytes of VRAM each. You started with zero fine-tuning experience. You now have the skills to take a foundation model, adapt it to a specific domain, evaluate it rigorously, and ship it to production in a way that's fast, cost-efficient, and maintainable. That's the complete arc, from basics to a running system. 3 concrete next steps worth your time. First, pick one domain you actually care about and apply these templates to it. The techniques land differently when the problem is real. Second, publish your fine-tuned models on Hugging Face Hub. The community feedback you get back accelerates your learning faster than any course can. Third, when you're ready to push further, the frontier right now is RLHF and constitutional AI for alignment, and scaling up to Llama 3 8B or Llama 370B for capability. The foundation you've built here transfers directly to both. The resources you'll return to most. The Unsloth documentation at docs.unsloth.ai for library-specific details. The Hugging Face Model Hub at huggingface.co models for pre-trained checkpoints and community fine-tunes. And the PyTorch documentation at pytorch.org/docs when you need to go deep on the framework. Every code example from this course lives in the course repository. Use it as a reference implementation, not just a learning artifact. Good luck with what you build next. This chart breaks down optimization techniques by two axes: raw throughput in tokens per second and the speed-up factor relative to an unoptimized baseline. The throughput bars show you absolute capacity, how much work each technique can do. The speed-up bars show you relative gain, how much better it is than doing nothing. Two techniques stand out clearly. Quantization and continuous batching both show substantial throughput gains over baseline. But notice that continuous batching and page attention lead on the speed-up axis. That distinction matters. Quantization makes your model smaller and faster per token. Continuous batching and paged attention make your serving infrastructure smarter about how it uses the GPU across many concurrent requests. In practice, you want both model-level optimization and infrastructure-level optimization because they target different bottlenecks and their gains are largely additive. Catching isn't one strategy, it's a hierarchy, and each layer targets a different type of repeated query. The exact match cache using Redis is the simplest. Hash the full prompt, store the response, set a 1-hour TLA, hit rate around 30%, latency under 1 millisecond. This works well for FAQ-style applications where users ask identical questions verbatim. The semantic cache using PG Vector goes further. Instead of matching exact strings, it embeds the prompt and retrieves responses for semantically similar queries, paraphrases, rewordings, near duplicates. Hit rate climbs to roughly 55% with about 5 milliseconds of lookup latency. The KV cache prefix sharing in VLLM targets a different bottleneck entirely: the time to first token for requests that share a common system prompt. By caching the key value attention states for that shared prefix, VLLM can skip recomputing it for every new request, cutting time to first token by 30 to 60%. Finally, CDN edge caching with CloudFront handles static, get responses at the network edge, keeping that traffic from reaching your inference servers at all. Layer these strategies appropriately for your traffic patterns, and the cumulative latency reduction is significant. Load balancing algorithms are not interchangeable. The choice has a measurable impact on both throughput and latency. The bar chart on the left shows effective throughput in transactions per second across several strategies. GPU-aware least busy tops the chart at 320 transactions per second. L4 TCP round-robin sits at the bottom at 150. Weighted round-robin based on capacity lands at 290. The line graph on the right shows why the gap exists. It tracks P95 latency over time for round-robin versus GPU-aware routing. Round-robin fluctuates. It sends requests to replicas without knowing their current load, so some GPUs get queued up while others sit idle. GPU-aware routing monitors actual GPU utilization and routes each request to the least loaded replica. The result is steadier, lower latency across the board. The practical takeaway: if your load balancer supports custom health metrics, wire it to your GPU utilization Prometheus endpoint. The throughput difference, 150 versus 320 transactions per second, is entirely free performance. No hardware changes required. This cost breakdown is for a real production deployment called Animux. And the pie chart makes one thing immediately obvious. 76% of the monthly bill, the dominant slice by far, is GPU compute. Everything else, CI/CD monitoring, bandwidth, storage, is noise by comparison. That single fact tells you where to focus your optimization energy. The trajectory graph on the right shows what happens when you actually apply the techniques from this lesson over 6 months. The red line, representing unoptimized spend, stays flat and high. The green line, representing optimized spend, declines steadily as caching warms up, auto-scaling tunes itself, and the spot-to-on-demand ratio gets dialed in. The gap between those two lines is real money. When you audit your own deployment, start with GPU utilization. If that number is below 70%, you are paying for idle compute, and batching or auto-scaling adjustments will close that gap faster than any other change you can make.